is to calculate the magnetic field in the center of a current-carrying arc.
Hey there, amazing students! Welcome to our exploration of one of the fundamental pillars of electromagnetism, the Biot-Savart law. Think about this. In our everyday lives, we're surrounded by invisible forces that quietly shape everything around us. From the way a compass needle dances to the hum of motors driving our tech gadgets, it's all connected to something called the Biot-Savart law. This law is like the behind-the-scenes magician revealing how electric currents and magnetic fields are best buddies. In this video, we will go into the principles that underpin this law, discovering the mysteries of magnetism and electricity. Get ready because things are about to get electrifying. Before we start the discussion about our topic, let us all take a look at the historic background of the Biot-Savart law. The Biot-Savart law, named after French physicists Jean-Baptiste Biot and Félix Savart, emerged in the early 19th century as a groundbreaking discovery in the field of magnetism. Their work was built upon earlier findings by Hans Christian Ørsted, who had demonstrated the relationship between electric currents and magnetic fields. Biot and Savart experiments and mathematical formulations provided a systematic way to calculate the magnetic field produced by a steady current in a wire. To highlight, they discovered that the magnetic field surrounding a current-carrying wire is dependent on the magnitude of the current, the orientation of the wire, and the distance from the wire. And now, let's move on to what Biot-Savart law really is. It says there, the Biot-Savart law tells us that when electric current flows through a wire, it produces a magnetic field around it. This magnetic field's strength and direction depend on factors like the amount of current flowing and the distance from the wire. To make it short, the magnetic field is dependent on the amount of current in a wire. The magnetic field B produced by a steady current I in a straight conductor is directly proportional to the magnitude of the current. However, additional factors such as the distance from the conductor and the orientation of the current-carrying conductor with respect to the point where the magnetic field is being measured should be considered when calculating for the exact strength of magnetic field.
The Biot-Savart law in its scalar form. The Biot-Savart law allows us to determine the magnetic field at some position in space that is due to an electric current. More precisely, the Biot-Savart law allows us to calculate the infinitesimal magnetic field that is produced by a small section of wire, carrying current I such that infinitesimal wire segment is collinear with the wire and points in the direction of the electric current as shown in the formula, where infinitesimal magnetic field equals permeability of free space I over 4 pi into infinitesimal wire segment times the distance over distance squared. In figure 1, the infinitesimal magnetic field that is created by an infinitesimal section of wire carrying current I. Note that the vector distance goes from infinitesimal wire segment to the point where we wish to calculate the field, where r, or the distance, is the vector from the element of wire to the point where we would like to determine the magnetic field, as illustrated in figure 1. The concept of proportionality is called the permeability of free space and has the value of permeability of free space equals 4 pi times 10 raised to negative 7 with the unit of Tesla times meter per ampere. Additionally, infinitesimal means that it is an indefinitely small quantity. We have seen that mass produces a gravitational field and also interacts with that field. The charge produces an electric field and also interacts with that field. Since moving charge, that is, current, interacts with a magnetic field, we might expect that it also creates that field, and it does. With that said, using Biot-Savart law, we are now able to determine the position in space with the help of the magnetic field at point P produced by the current carrying wire. Here in figure 12.2.1, a current element, I infinitesimal wire segment, produces a magnetic field at point P given by the Biot-Savart law. The equation used to calculate the magnetic field produced by a current is known as the Biot-Savart law. It is an empirical law named in honor of two scientists, namely Jean-Baptiste Biot and Félix Savart, who investigated the interaction between a straight current-carrying wire and a permanent magnet. This law enables us to calculate the magnitude and direction of the magnetic field produced by a current in a wire. The Biot-Savart law states that at any point in figure 12.2.1, the magnetic field due to an element infinitesimal wire segment of a current carrying wire is given by the equation of infinitesimal magnetic field equals permeability of free space over 4 pi into current carrying I infinitesimal wire segment times distance over distance squared. The Biot-Savart law in its vector form. The vector use of the Biot-Savart law has some similarities with the Coulomb's law. To calculate the electric field, as the magnitude of the magnetic field decreases as the inverse of the square distance between the source and the field. However, it can only be expressed in differential form, i.e. as an infinitesimal, and it requires working in 3 dimensions because of the cross product. It is usually more convenient to use the Biot-Savart law in the form infinitesimal magnetic field equals permeability of free space, current carrying wire, over 4 pi into infinitesimal wire segment times distance over r cubed, where the unit vector r hat was replaced by r distance.
How to apply Biot-Savart law. To solve for the Biot-Savart law problems, the following steps are helpful. Number 1. Identify that the Biot-Savart law is the chosen method to solve the given problem. If there is a symmetry in the problem of comparing magnetic field and infinitesimal wire segment, Ampere's law may be the preferred method to solve the question. Number 2. Draw the element length infinitesimal wire segment and the unit vector or the distance, noting that the infinitesimal wire segment points in the direction of the current and the distance points from the current element toward the point where the field is desired. Calculate the cross product of the infinitesimal wire segment and the distance. The resultant vector gives the direction of the magnetic field across the Biot-Savart law. For the fourth, use the equation below and substitute all given quantities into the expression. To solve for the magnetic field, note all variables that remain constant over the entire length of the wire may be factored out of the integration. For the fifth and last, use the right-hand rule to verify the direction of the magnetic field produced from the current or to write down the direction of the magnetic field if only the magnitude was solved for in the previous part. And now we will proceed to the example of a Biot-Savart law problems. Calculating magnetic fields of short current segments. 1. A short wire of length 1 cm carries a current of 2 ampere in the vertical direction shown in figure 12.2.2. The rest of the wire is shielded so it does not add to the magnetic field produced by the wire. Calculate the magnetic field at point P, which is 1 meter from the wire in the x direction. So here's the strategy used in the problem. We can determine the magnetic field at point P using the Biot-Savart law. Since the current segment is much smaller than the distance x, we can drop the integral from the expression. The integration is converted back into a summation but only for a small infinitesimal wire segment, which we now write as the change in current segment. Another way to think about it is that each of the radius values is nearly the same. no matter what where the current element is on the line segment. If the change in current segment is small compared to the x, the angle theta is calculated using a tangent function. Using the number given, we can calculate the magnetic field at P. So here's the solution for the given problem. The first step, the angle between the change of current segment and distance is calculated from trigonometry, knowing the distances I and x from the problem. Theta equals tan raised to negative 1 times the quantity of 1 meter over 0.01 meter is resulting to 89.4 degrees. After we get the angle theta, we can now solve for the magnetic field at point P using the Biot-Savart law. By using all the given and translating it into the magnetic field equation of the Biot-Savart law, we can now arrive in our answer, which is 2.0 times 10 raised to negative 9 Tesla. For the last step, using the right-hand rule, from the right-hand rule and the Biot-Savart law, the field is directed into the page. Now let's proceed to the significance of solving this problem. This approximation is only good if the length of the line segment is very small compared to the distance from the current element to the point. If not, the integral form of the Biot-Savart law must be used over the entire segment to calculate the magnetic field.
The real-life applications of the Biot-Savart law are the following. First is to calculate the magnetic field in an indefinitely long straight wire owing to a constant current. Next is to calculate the magnetic field in the center of a current-carrying arc. Next is to calculate the force between two parallel and lengthy current-carrying conductors. Lastly, to calculate the magnetic field along the axis of a circular current-carrying coil. Here is a video animation of the Biot-Savart law.
On April 21, 1820, Danish physicist Hans Christian Ørsted noticed that a steady current-carrying wire can deflect a nearby magnet. If the direction of the electric current changed, the magnet appeared to get deflected towards the other side.
After ng ilang test and experiments na ginawa ni Hans Christian ay napagtanto niya na ang isang steady current carrying wire ay nakakapag-produce ng isang steady magnetic field. So para malaman natin kung ano yung direction ng magnetic field ay isipin natin na hawakan yung wire and kung saan nakatutok yung thumb natin ay dun yung direction ng current while yung other four fingers naman natin ay yun yung direction ng magnetic field.
Two French physicists, Jean-Baptiste Biot and Félix Savart, gave the complete mathematical tool to calculate the magnetic field. Thus, it is known as the Biot-Savart law. In this animation video, we shall first consider the scalar form of the Biot-Savart law, and thereafter discuss the full vector concept on this. To build a realistic concept on Biot-Savart law, let us first imagine a wire. It carries a current of amount I. Also, imagine a point, P, near the wire. All portions of the wire have their contributions in generating a magnetic field at this point, P. A is an arbitrary point on the wire. A portion of the wire is taken about the point, A. This portion is named dl. Let us concentrate on this portion of the wire, dl, about the point, A. Distance between point A and point P is r. We shall now calculate the magnetic field at point P due to this small portion of the wire. So, let's start. If the produced magnetic field at P is dB, then Biot-Savart law says dB is proportional to I, the amount of current flowing through the wire, to the length of the portion of the wire, which is dl. 2. Sine theta, where theta is angle, formed by dl and r. R is the distance, AP. And dB is inversely proportional to the square of r. Summing up all these, we get the complete scalar form of Biot's Savart law, which is dB equals mu0 by 4 pi into I dl sine theta by r square. Mu0 is the magnetic permeability of free space. Here, in this case, the direction of the magnetic field is not clear. To get its direction, we need to explain the vector form of the law. And here it is. The vector form of this law is written like this. Note that there are arrows over the letters of dB, dl, and r. They indicate that there are three vectors in this equation. You must be aware that any vector has two parts: magnitude and direction. On this page, this arrowhead, m, is a vector. Its value, or magnitude, is m. And cap m is its direction. For example, let the gravitational force acting on a 1 kilogram object be F. This vector, F, has two parts. First one is its value, or magnitude, which is about 9.8 Newton. And the second one is its direction, which is downwards, or towards minus cap z direction. After noting all these, the Biot-Savart law can be written like this. Here, dl and cap dl are the magnitude and direction of the vector dl, respectively. And r and cap r are the magnitude and direction of the vector r, respectively. The direction of dB is the cross product of cap dl and cap r. If we calculate the cross product, we get sine theta into cap dB, where cap dB is the direction of the vector dB, and it is perpendicular to the plane that contains vectors dl and r. So, we understand that cap dB is perpendicular to this plane. But to which direction? Upwards or downward? To realize direction of a cross product, imagine a right-handed screwdriver. Almost all of us are aware of a right-handed screwdriver. On a horizontal plane, if we rotate the screwdriver in clockwise direction, the screw should go downwards. That is, clockwise rotation yields downwards direction. Again, if you rotate the driver in anti-clockwise direction, the screw moves upward. Thus, anti-clockwise rotation gives upward direction. In this cross product, we need to rotate from the first vector, dl, to the second one, r. Of course, through the shorter angular path. And thus, we get its direction to be downward. Actually, two angles are there between the vectors dl and r. One of them is smaller, and a larger another one. We are to move through the smaller angle. Hence, we get a clockwise rotation here. Thus, the direction of this product vector is downward. Now let's change the direction of the electric current. In that case, the direction of dl will be opposite, and angle between them is pi minus theta. Multiplying cap dl cross cap r, we get sine pi minus theta into cap dB. Sine pi minus theta is equal to sine theta. And the direction of the dB is now upwards. Thus, if we switch direction of the current, the direction of dB also changes. This time it should be completely opposite to its previous direction. Hope you realize that law. Please reply if you understand this topic.